I'm going to try to do one podcast for note cards 50 through 55. It's a basic review of logarithms. Okay? And here we have, this is note card 50, the natural base e. And I'm just going to kind of read through this and tell you a little bit about e and what you need to really know about it. The irrational number e is approximately 2.7182, but since it's an irrational number, it's going to go on forever, indicated by these dots. Introduced by Euler in 1727, is used for the base of some exponential functions. Because f of x equals e to the x, this exponential function with base e and x is in the exponent, has special calculus properties that simplify many calculations. E is called the natural base of exponential functions for calculus purposes only. E is derived by this limit. And basically what it's saying here is that you take this function 1 plus 1 over x to the power of x. As x approaches infinity, is going to approximately be, or it's going to converge on the number e. As x gets larger, again it approximates to 2.71828 and so on and so forth. E is a number like pi in that it is such an important number that the letter e is used to represent the number instead of using its decimal approximation. And basically that's what you need to really know about e right now, is that it's a number and its approximation is 2.7182, and instead of writing that down we always use the letter e to represent that, just like we use the pi sign to represent the number 3.14. Okay? Okay, note card 51, graphs of exponential and logarithmic functions. Here we have the function y equals e to the x, which is an exponential function. The base is e, the exponent is x. Since the exponent is a variable, that's why we call it an exponential function. The graph of this function looks like this. You should be somewhat familiar with this because of Algebra 2. You should also be somewhat familiar with this because we had this in our parent functions assignment at the beginning of the year. It has a horizontal asymptote as y equals 0, and this limit statement is read like this. The limit of e to the x as x is approaching negative infinity is equal to 0. In other words, as I keep going left to negative infinity, this function is going to get close, 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 close. The limit is 0. Okay, but there's the graph. Then we have y equals ln x. A couple things you should probably write right here. Ln x, this simply means the natural log. We call it the natural log. And the reason we call it the natural log is because it can really be written like this. Log base e of x, because remember e is the natural base. So this is the natural logarithm, but you will hardly ever see it as log base e of x. You will see it pretty much all the time as ln x, in other words the natural log. Now when we work problems using ln x, I will probably tell you that it might be easier for you to see it if you will write it in this form, log base e of x. Okay. The graph of the natural log looks like this. Has a vertical asymptote at x equals 0. The limit of ln x, or the natural log of x, as x is approaching 0 from the right. If x is approaching 0 from the right, it's where my little pencil is going. I'm approaching 0 from the right, and as my function approaches 0 from the right, the function itself heads off to negative infinity. Y equals e to the x and y equals ln x are inverse functions, and you should be able to see that from their graphs. If I give a rough sketch of what we had the graph up there, kind of look like that. They are reflections, or they're symmetrical in the line y equals x, if I can draw it right. You should be able to tell without a doubt just by looking at their graphs that they are reflections in the line y equals x, or they have symmetry in the line y equals x, and that's why you can tell from their graphs that they are inverse functions. So ln x and e to the x are inverse functions. Note card 52, logarithms. A logarithm is an exponent. Log base e of x, that's how you would say that, log base e b of x is equal to a. This right here looks like it's a spelling error. It's if and only if. This means if and only if. Okay, so log base b of x is equal to a if and only if b to the power of a is equal to x. Here's how this works. B is the base here. B is the base here. They're the same. B to the power of a is equal to x. And we're going to go ahead and establish that x is greater than 0, b is greater than 0, and b is not equal to 1. Here's some examples. Log base 5 of 25 is equal to 2 if and only if 5 squared is 25. Again, 5 squared is 25. Log base 3 of 81 is equal to 4 if and only if 3 to the power of 4 is equal to 81. And finally, log base 2 of 1/8 is equal to negative 3 if and only if 2 to the negative third power is equal to 1 over 8. And hopefully you can see that that's true from a review from your negative exponents, that this is 1 over 2 to the third, which is 1 over 8. Some basic properties. Again, where b is greater than 0, b is not going to be equal to 1, and x is greater than 0. Log base b of 1 is equal to 0 because b to the power of 0 is equal to 1. B to the power of 0 is equal to 1. Anything to the power of 0 is equal to 1. Example, 2 to the power of 0 is 1. Number 2, log base b of b is equal to 1 because b to the power of 1 is equal to b. Hopefully you can see how I'm modeling this for you as how you're going to change it to an exponent. We will be having some exercises of changing logarithms to exponents and exponents to logarithms. 3 to the power of 1 is equal to 3. Number 3, b to the power of a is equal to b to the power of a. Example, 4 to the third is equal to 4 to the third. Number 4, what you need to know here is you need to remember that when we're talking about an exponential function and a logarithm, they are inverse functions. They undo each other. Just as multiplication undoes division when you're solving an equation, or addition undoes subtraction, a logarithm will undo an exponent, and an exponent will undo a logarithm. So what I have here is b being raised to the power of log base b of x. And since the base here is the same as this base here, what happens is all we have left is x. Because if you raise a base to a logarithm of the same base, all you have is basically this argument left inside, x. It undoes each other. Common logarithms. Again, a logarithm is an exponent. And what we mean by a logarithm is an exponent. It's an exponent written in a different manner. Here we have log x is equal to a if and only if x is equal to 10 to the a. What this is saying is a common logarithm is the logarithm base 10. And on your calculator, the little button on the left-hand side of your calculator, that is log base 10. Okay? So this is 10 to the a equals x. 10 to the a equals x. We have a common base 10. Here's some examples. What you will see, first of all, when you deal with log base 10, you don't have to write the 10. Okay? If you don't see a base there, then you assume it's base 10. So 10 to the third is equal to 1,000. 10 to the third is equal to 1,000. 10 to the power of negative 2 is equal to 0.01. And just remember that 0.01 is equal to 1 over 100, which is the same thing as 10 squared. Basic properties. Let x and y be real numbers with x greater than 0. Here you should be able to see that 10 to the power of 0 is 1, because if it's if the base is not there, it's base 10. 10 to the power of 1 is equal to 10. 10 to the power of 1 is equal to 10. 10 to the y is equal to the power of 10y. Now, if it helps you out, do like I'm doing. Write the 10 there. 10 to the power of 0 is equal to 1. 10 to the power of 0 is equal to 1. 10 to the power of 3 is equal to 10 to the power of 3. And let's look at this example right here. 10 to the power of log base 10, because there's no base written there, that's going to be base 10. So again, what do we have is we have that you have log base x is equal to log base x. You could also say that x is equal to x, because what's going to happen here is the base is 10. It's being raised to a power of a logarithm with the same base, and so what you really have is this is equal to this. X is equal to x. Here the same thing happens. Base 10 raised to a power of logarithm base 10 of 6. So what we have is 6 is equal to 6. Okay? Some basic properties there. And this note card was the same as the previous one. The only difference is the previous note card was ln, which is log base e, and they had the same properties. This one is log base 10, has the same properties, just two different bases. The other note card had a base e. This note card has base 10. Continuing on. I believe this is note card 54. Natural logarithm. A logarithm is an exponent. Didn't we already cover this? Or we haven't covered this one yet. This is exactly, I got ahead of myself. Some of these were the same up here. Yeah, this was for any exponent. I'm sorry for any base b, any base down here. The previous one was the common logarithm base 10. This one is the common logarithm ln x, which is going to be log base e. So this is log base e of x is equal to a, is another way of writing it. because e to the a is equal to x. Okay? And it's going to have the same properties as what we've been talking about. If it helps you out, rewrite it as log base e equals 0. Log base e of 1 equals 0. I just replace the ln with log base e. So e to the power of 0 is equal to 1. E to the power of 0 is equal to 1. Sure it is, because anything to the power of 0 is 1. Here I have log base e of e is equal to 1. I just replace the ln with log base e because that's what ln is. It's the natural log. It's the logarithm base e. So e to the power of 1 is equal to e. This should say e. Okay, continuing on. Log base e of e to the y is equal to y. Well, sure, because e to the y is equal to e to the y. Here we have log base e of e to the 4th is equal to 4, because e to the 4th is equal to e to the 4th. And then finally, again, we have a base being raised to a power of a logarithm with that same base. So what do we have? We would have x equals x. And finally, note card 55. Basic properties of logarithms. We have a product rule. If you have a logarithm of certain base of something being multiplied, you can break this into two pieces right here with addition. You can expand multiplication with addition. So this becomes log base b of r plus log base b of s. The example here, I have log, there's no base indicated here, so that's base 10. You don't have to write it, but you do need to know that it's base 10. Of x times x plus 1. So I can expand this multiplication here with addition. This becomes log of x plus log x plus 1. And of course they're base 10s. So here I have ln 3 plus ln x plus ln x minus 2. Well, if I can expand multiplication with addition, then I can condense addition with multiplication. This becomes ln of 3 times x minus 2. Again, if I can expand multiplication with addition, then I can condense addition with multiplication. Now the quotient rule, if I have a logarithm of some base and something being divided, I can expand that with subtraction. So log base b of r divided by s becomes log base b of r minus log base b of s. Okay, here's the example. I have ln, log base e, and I can just leave that as ln. Okay. The only reason why I was having you write log base e before, because when you're changing from one to the other, it might be easier to be able to see that that's log base e and go through those steps I was showing you. ln of x plus 1 divided by x, I can expand this with subtraction. This becomes ln of x plus 1 minus ln x. Example 2, I have log base 10 of 30 minus log base 10 of 5. So if I can expand division with subtraction, then I can condense subtraction with division. So this becomes log base 10 of 30 over 5, which is log base 10 of 6. Power rule. if I have a logarithm here, log base b of r to the power of c, well, what can happen with this c is it can come out front of the logarithm and become the coefficient of the logarithm, or the number in front there. So this becomes c times log base b of r. So here I have log base 10 of x to the power of 4. This 4 can come to the front and become 4 times log x, and that's it. Log base 10x. It's pretty simple. The power just comes out front. And sometimes it might be beneficial to be able to take this coefficient and make it a power, because if I can do it one way, I can go back the other way. Here I have 3 in front, so if I'm condensing this or writing it in its simplest terms, this would become ln, or log base e, of x minus 2 to the third power. And that's how the power rule works. Pretty much all of this is review from Algebra 2. Hopefully it wasn't too difficult. I'm going to give you some assignments so we can practice and hopefully make more sense of this if it's a little bit fuzzy.